So we are moving on. We're moving on from ionic compounds to molecular compounds. Now, inside molecular compounds, there are two different kinds of subgroups, let's say. And we're going to talk about both today. Now, one thing that is going to be useful for us is that, first of all, naming molecular compounds of the first kind, the binary kind that we're going to talk about first, is actually really easy. The only difficulty really is A, recognizing the structure, and B, memorizing the prefixes. And so we'll get into that in just a second. The other type of molecular compound is going to actually be kind of a blending of molecular compound and ionic compound nomenclature. And so the naming of acids depends very much on our ability to recognize ions. And so we're coming back full circle to ions again, and I'll show you how you can name acids based off of ions, and that'll be the last thing that we do before we head off into this hopefully very nice weekend, at least based off of what's going on outside right now. So let's start off with molecular compounds. Molecular compounds we can recognize very easily. We've got two nonmetals. And so from a standpoint of variety, there isn't as much variety in molecular compounds as there is in the ionic compounds, at least from based on the kind of the limited structure that we're putting on it. And as far as that goes, we're gonna basically talk about binary compounds and acids. Binary compounds, they follow a very easy kind of formula. Prefix element, prefix element I. So the first part, the element and the element I, that should sound a little bit familiar to you because that was basically the structure that we used for ionic compounds that were binary as well. Potassium chloride, tin oxide. They followed the same kind of pattern. Element, element I, element, element I. What separates the molecular compounds is prefixes. Now, where do those prefixes come from? Well, this is where it can get a little bit confusing because this is where it departs from ions. We're not talking about charges here. The prefixes tell us how many of each element are there. And so the prefixes are here as follows. Mono, di, tri, tetra, penta, hexa, hepta, octa, nona, and deca. Now you look at this list and you say, okay, that's 10 different prefixes. One thing that you should hopefully recognize, however, is that most of these prefixes are prefixes that you have seen before. Geometric shapes follow most of these kinds of forms. A three-sided object is called a triangle. Tri for three, angle because it's got three angles inside of it. A five-sided object is called a pentagon. Penta for five. A six-sided object is called a hexagon. Hexa for six. An eight-sided object is called an octagon. Octa for eight. And so on. The ones that are kind of unusual, let's say, are the ones that don't seem to follow a pattern that we're familiar with. So, for example, tetra. Tetra for 4 instead of quadra. Hepta for 7 instead of septa. Di for 2 instead of bi. But those are really the only ones that are unusual. Now, why these particular prefixes instead of others? Origins. All of these prefixes come from Greek origins, and that's why it's hepta instead of septa. That's why it's tetra instead of quadra. It's a consistency in the language here. We're using Greek for all of the prefixes of numeric origin here. And so these prefixes we attach to the element's name to tell us how many atoms of that element are present in the molecule. So if I put mono on the name, it tells me that there's one of that element. If I put octa on the name, it tells me that there are 8 of that element. And so we can go directly into chemical formulas based off of these prefixes. There are a couple of exceptions that we do want to pull out, however. One of the exceptions is that if the first element is 1, we don't need to say mono for it. In that particular case, the mono can be assumed. So, for example, CO2, we don't need to say monocarbon dioxide. We can just say carbon dioxide because that 1 is presumed for the carbon. So that's the first exception. If the first prefix is mono, we can leave it off. The second exception is a linguistic exception. And what I mean by that is it is an exception we take when the word that we are trying to say will come out awkwardly. And again, primarily focuses on oxygen. If a prefix ends in a vowel and the base name starts with a vowel, that first vowel is often dropped. Now, where we see this most often is with things like monoxide. So instead of saying monooxide, we drop off one of those O's to prevent that double O sound. Because we know in English, double O isn't OO, it's oo. And carbon monoxide doesn't sound quite right. So in that case, to avoid that double O sound and confusion over it, one of those O's gets dropped off. Monoxide ends up being the name from that. And that's really the place where we see it the most often, because in most other cases, that double O sound, that double vowel sound, we usually can parse out relatively easily. So dioxide, we don't need to take off one of those or the other. We can say both vowels consecutively and it's okay. Triiodide, same thing. So those are the primary exceptions around this molecular naming system. If the first one is mono, we don't have to say mono. If we end up with a double O sound or an OA sound, we can omit one of the vowels. Let's take a look at some examples. So in our first example, AS3Cl5, we should recognize AS is arsenic, Cl is chlorine. Those are the two elements that we are dealing with. Now let's add prefixes and change the ending. Prefix for 3 is tri, so this is tri-arsenic. Prefix for 5 is penta, so penta. And we need to change the INE to IDE, so pentachloride is the result. So AS3Cl5, the proper name for that is triarsenic pentachloride. For our second example, IBR. I is iodine. Br is bromine, so we're going to change that to bromide. We just need to add prefixes. Prefix for 1 is mono. Since it's the first element, though, we don't need to say it. So iodine stays as iodine since there's only one of them. We also have 1 bromine, so mono goes in front. Iodine monobromide is the correct name. Our last example on this slide, we've got sulfur, and we have oxygen, which we would call oxide. We just need to put the appropriate prefixes on. Prefix for 4 is tetra. So tetra, sulfur. The prefix for 8 is octa. So tetrasulfur octaoxide would be the result here. Now, this is an example of another kind of possible vowel dropping exception here. It is possible you could see this as oxide, dropping the A off of it, just to avoid that AO diphthong there. Not consistently applied. You do see both, but that is a possible place for it. Any questions with these 3 examples? All right, I've got a couple for you to try then. So the first one is N2O2. The second is S2Br7. So write the names of these 2 compounds in succession. So name the first one, put a comma, name the second one. and we'll see how we're doing in a couple of minutes. All right, so for this first one, we've got nitrogen and we've got oxide. That would be the kind of two starting bases. What's the prefix for two? Di. And since it's two for each of them, then the same prefix would go with both, dinitrogen, dioxide. Any questions with that first one? All right, for the second one, we've got sulfur and bromide. What are the prefixes here? So prefix for two, we already have established, it's di. So disulfur is the first word. What's the prefix for seven? Hepta. So S2BR7 would be disulfur heptabromide. All right, any questions with that one? Okay. So I think one of the more complicating things that we ran into with ionic compounds was when we started to turn it around and go from name to formula, we had to concern ourselves with charges and crisscrossing and all that other stuff. Here, we don't have to worry about that so much because since the prefixes give us the subscripts, all we have to do is basically just translate it down. So this becomes a relatively simple exercise for us where we are just literally taking the prefixes and the symbols and basically just dissecting the words. So dichlorine, so I've got two Cl's, non would be 9 oxygens. So the formula for that is Cl2O9. If I break down this second example, tetra is 4, phosphorus is P, tri is 3, Chloride is Cl. The chemical formula here, P4Cl3. So I literally just take that name and I just dissect it, interpret what the prefixes mean, and just turn them into the subscripts on that element. And so this is what I was talking about when I said molecular nomenclature is a lot simpler. So I don't have to worry about charges. I don't have to worry about charge balancing. I don't need to worry about polyatomic ions. I don't have to worry about any of that. The name gives me the formula. The formula gives me the name. I just have to remember what those prefixes are. That's really the only complicated thing in this, is remembering what those prefixes are. So give you an opportunity to try some more here. 3 compounds. Put in the formulas for those compounds. Separate each formula using a comma. All right, let's break this one down as well. So dinitrogen, di means 2, nitrogen is N. Pent means 5, oxygen is O. So N2O5 is the name of this, is the formula for this compound. Tri is 3, chlorine is Cl. Octa is 8, iodide is I. So Cl3I8 is the formula for that one. And then finally, chlorine. The fact that we don't have a prefix on it means that it is 1. So 1Cl, tri is 3, sulfide is S. So ClS3 would be the correct formula there. Would it be incorrect to say Cl1S3? No, it wouldn't. In fact, in your homework, it's going to require you to put 1s in for some of the answers, just so that it recognizes that you got the formula correct. So just be aware of that when you're doing some of those ones where it's going to be like this and it asks you for a string of numbers connected by commas. If the number is 1, make sure that you put in a 1 for those and you don't just leave it blank. All right, any questions with these? All right, so that's nomenclature for binary molecular compounds. Like I said, it's pretty straightforward. It's relatively simple, and that's good for us because that means that it should be easy to identify, easy to name. The other half of this is talking about molecular compounds that are acids. What makes acids unique is that acids are substances that are molecular compounds, They are primarily composed of nonmetals. But when they dissolve in water, they actually split apart into ions, just like an ionic compound does. So acids kind of exist in that really weird world between ionic and molecular compounds. And the reason why they exist in that particularly weird world is because they're hydrogen based. Now, if you look at hydrogen on the periodic table, you see that hydrogen is, even though it's non-metallic, it's shown here with the alkali metals. Why is it shown with the alkali metals? Primarily for this reason. In certain situations, hydrogen is going to act like a metal in the sense that it's going to form positive ions and give away its electrons. Now, the way that we can spot acids by their formula is we look for compounds that have hydrogen as their first element. If we see hydrogen as that first element in our compound, that immediately should trigger in our minds, this is an acid. And because it's an acid, I need to treat it differently from my other concepts of naming. Now, inside of acids, we can break it down into different groups. We can talk about binary acids, that is hydrogen with another element. We can talk about oxoacids, where we have hydrogen and a polyatomic ion. For the purposes of talking about naming here, we're going to largely avoid this classification system. The reason we're going to avoid this classification system when it comes to naming is because naming acids doesn't fall into this binary system. Naming acids actually falls into a threefold system. The threefold system of naming acids has everything to do with what is attached to that hydrogen in that compound. And so this is where we want to think about acids, even though they are molecular, we want to think about acids as ionic compounds. Even though technically they aren't, they kind of exist in that in-between world. We want to think about them as ionic compounds because that is ultimately going to be how we are able to identify and classify and name them. And the process is relatively simple. I need to look at what is attached to that hydrogen and what the name of the ion attached to that hydrogen is. Because that's ultimately going to tell me which one of these three slots it fits into. So, if my anion, if the thing attached to hydrogen, if its name ends in IDE, fluoride, chloride, bromide, the name of that acid is going to be hydro whatever ic acid. So if I'm dealing with fluorine, hydrofluoric acid. Bromine, hydrobromic acid. Chlorine, hydrochloric acid. This also applies to other ions that end in IDE. So for example, cyanide. Cyanide is Cn minus. It isn't binary, it's polyatomic, but it ends in IDE. And so how do we name an acid built off of cyanide? Same way, hydrocyanic acid. So if that ion ends in IDE, it's a hydroic acid. And that thing that fits between the hydro and the ic is basically the root of whatever that ion was. Or brome, sulfur, phosphor, whatever. These other two categories are basically surrounding what are traditionally called oxoacids, and that is the polyatomic ions that have oxygen. And those polyatomic ions that have oxygen in them basically fit into two categories. There are the eights and there are the ites. The eights tend to have more oxygens on them. The ites tend to have fewer oxygens on them. But all of the eights are named as follows. Whatever the root is, then ic acid. So if I have the sulfate ion, sulfate acid is sulfuric acid. Phosphate acid, phosphoric acid. Chlorate acid, chloric acid. Acetate acid, acetic acid. So if I can identify that polyatomic ion as ending in ATE, it's going to be an ic acid. If I can identify that ion as being an ite acid, so chlorite, bromite, hypochlorite, hypobromite, hypoiodite. All I do is change the ite to plus acid. So chlorite ion becomes chlorous acid. Nitrite ion becomes nitrous acid. So ultimately, when we are naming acids, we're looking to fill one of these kinds of slots based upon the name of the ion itself. And so it really becomes a matter of, and I hate saying this because I feel like I keep reiterating the same point this week, you have to know your polyatomic ions list. Because this becomes a matter of recognition. I look at this and say, okay, hydrogen's the start. I know it's an acid. What's attached to the acid? Okay, that's the acetate ion. So 8 becomes ic. This is acetic acid. The only way I know that is I have to know ions. And unfortunately, that is the toughest task out of this entire chapter, is having that working knowledge of these ions. And I mean, it's for that reason. The quiz that you just took originally, the version that I had was given, originally had the naming of ions as part of that quiz. I took that off because I didn't think 3 days was sufficient time to memorize a bank of ions. You'll see all of that stuff when we do the nomenclature quiz, which is quiz 7. You'll see it then. But I didn't think it was fair for you to see it today. So this is something that is going to be part and parcel for the process over the next 2 to 3 weeks. All right, let's take a look at some other examples here. Again, it comes down to recognition. All of these begin with hydrogen, so I know that they are all acids. It comes down to the recognition. So CN, I have to recognize that as cyanide. Cyanide means that I am in the hydro. So hydrocyanic acid is the name of this. For the second one, NO2, I have to recognize NO2 is nitrite. Now, just again, a little trick on this one. Polyatomic ions that have two oxygens are always going to be ites. Polyatomic ions with one oxygen are usually hypoites. There's one exception to that. It deals with cyanate. Not worth getting into because that's not even on the list for you guys to memorize. So we'll ignore that one for that. If I've got two oxygens, I know it's an ite. It can't be anything else. There's no such thing as an ate with two oxygens. Ates either have three oxygens or four. And most of them have three. So this is nitrite. Ites get turned into us's. So this is nitrous acid. Finally, we get to this one. We know it's a phosphor. Question is it a phosphate or a perphosphate? I have four, it's either one. Phosphate is one of the few that has four as its ate without the per on it, so this is just the phosphate ion. Since it ended in ate either way, we knew it was going to be an ic acid. The name of this is phosphoric acid. All right. One final note before we put this away for the weekend. If you have to reverse the process, treat it the same way that you would for an ionic compound. Only it's a little bit simpler because H plus is always the cation, and since it is always the cation, the only subscript that is going to change is the one on the H. Because if the negative ion's 2 or 3 negative, I'm going to need to add more H pluses to compensate. So you're basically going to take the name and reverse the process, find the name of the substance, turn it back into an ion, add the appropriate number of hydrogens to compensate. But that's what you're going to end up doing overall. On your way out, get that last participation point. Tell me how you're feeling about this one. Don't forget about the assignments over the weekend. So 5-2 is all about naming covalent and acid substances. And don't forget about the pre-assignment. Technically due before class starts on Monday, but probably a good idea to do Sunday night and not Monday morning. Have a good weekend.